Okay, next I'm going to define a very important concept called white noise. Okay, this is an important concept in many applications, not only in communications, but also in control theory and in detection and estimation problems. So a white noise is a zero mean, white sense stationary random process if the random process has a flat PST. Okay, what does that mean? A flat PST means it has the same value for all frequency values. That indicates, okay, the power that the signal carries is equally distributed to all frequencies. Okay, not any frequency is favored. When you look at every specific frequency, every frequency band, when you look at it, based on the interval of the frequency band you look at, it will have the same amount of power allocated on that band, proportional to the interval length. Okay, but here, of course, we are dealing with, in general, in reality, we are dealing with um, band limited white noise. Well, this is a typical PST of a white noise. Okay, here you see the PST is flat, but of course only on this interval from minus W to W. This is what we call the band width of this white noise. Okay, and the power is the average power this white noise carries is equal to N0 times W, assuming that the amplitude of the PST is N0 over 2. Since the bandwidth is 2W, multiply them, the area under the PST gives you the average power, which is N0 times W. Okay. If you take the inverse Fourier transform, you obtain the autocorrelation function, and the autocorrelation function turns out to be what we call the sinc function. Okay. Some of you might be familiar with this function. Essentially, this function, as you can see from this expression, is defined as sinc of x is, well, if you look at this, you have 2 wt tau here, and you have 2 pi wt here. So that is essentially sine pi x divided by, and you have 2 pi tau here and just w here. That means you should have pi x here. So this is the definition of the sinc function, and this two is a famous couple of Fourier transform pairs. This is what we call usually the rect function, because it's a rectangular function on a bounded interval, and the rect function has the Fourier transform the sinc function, and the sinc function has the Fourier transform the rect function. So they are a Fourier transform pair, and in this specific context, the PST of a white noise is a rect function on the interval from minus W to W. That means the autocorrelation function is a sinc function whose peak value is N0 times W, because, well, you see Rx0 should give you the average power, which was found here. This should appear here as expected. And also, it crosses 0 at intervals of 1 over 2W. So this is 2 over 2W, this is 3 over 2W, this is 4 over 2W, and so on, also on the negative side. Okay, so this autocorrelation function, what does it tell you? It tells you that the correlation between observations, when the observation separation increases, the autocorrelation goes to 0. So you see a fast decay here in the envelope. So the correlation between observations, when you set them apart further and further, the correlation goes to 0. Okay, so as close as the observations are, the more correlated they are. Okay, and as I said, this is the real case. This is what we call white noise, but we also have a concept of ideal white noise. When this W is taken to infinity, okay, then that means your PST will be, let me put it here, your PST will be just this. Okay, it's a flat function over the entire real line, this frequency domain. Okay, And the sync function in this extreme becomes the impulse. Okay, if you remember, this here was 1 over 2w. 1 over 2w is just the first crossing. And as w goes to infinity, this goes to 0. So the sync function gets narrower and narrower. And at the extreme, at the limit, as w goes to 0, it becomes confined to 0. Okay, it becomes just an impulse. So autocorrelation being an impulse, what does it mean? Any observation of this random process is correlated only with itself. Okay, when you move just slightest in the time domain, the correlation disappears. Okay, so at distinct time instants, the observations you see are going to be, in general, independent, not only uncorrelated, but they are also going to be independent. Okay. Now, this is a mathematical abstraction because ideal white noise has infinite power. So in real life, it doesn't exist as a physical phenomenon, right? Because, well, the area under the PST is the power. And as you see, when W goes to infinity, the power goes to infinity. So it doesn't exist in real life. After some frequency, it will die out, certainly, okay? But for our applications, this ideal white noise abstraction is quite useful because in mathematical analysis, it's very easy to use. It's quite uh, good for derivation because it makes things very simple. And the thing is, um, even if the real noise is not ideal in the sense that it decays after some point, it can be assumed ideal because usually the bandwidth of this noise is going to be um, larger than the system we are dealing with. Okay, let's say you are dealing with a communication system that will operate in this region. So if your noise dies out after these frequencies, it doesn't concern you because you are not working there, right? Because it will only affect this band for you. That is your focus. Therefore, you can simply assume your noise to be ideally white. That means it's flat for every possible frequency value. And the autocorrelation is perfectly impulsive. So it makes computations very, very easy. You dealing with just an impulse is much more fine than dealing with the sync function, and the computations becomes much more easier. So we prefer to use ideal white noise in a lot of applications. Okay, it's very useful in modeling, especially noise in communication channels. And if you have a communication background, you should know this quite well.